So,
excuse me.
yes.
Can we ask questions now or?
Yes, please
Yes,
ask
sorry.
questions now and tell me things. I mean, if there is something that takes more time, I will then explain it later. But give me suggestions, whatever you want to learn, or I mean, take the opportunity.
Yes. Just one minor question. So, if isn't when you say the cutoff of the effective theory should be less than or equal to G and Planck, and considering that G has a running with energy, it's a little vague for me how that behaves.
Okay, very good. That's a good question, actually. Yeah, so let me write it here. The first question of today. I'm telling you that the cutoff of the EFT behaves as G and Planck, but G is a parameter that can run with the energies. So you could ask, at what energy are you evaluating this, or how does it change, or what's going on? No? And this applies actually for all the bounds that I'm giving you. Like, for example, that the mass is smaller than G and Planck. Also, the mass and the gauge coupling can get renormalized. And actually, this is quite surprising because the gauge coupling in 4 dimensions gets a logarithmic running, while the mass could get a quadratic correction. So how come is this stable under RG flow? Okay, it seems that you could violate it by going to the deep IR. Now, the point is, so typically, the short answer, I will give you a short and a long answer. The short answer is that you have to evaluate this at the same scale. So at a given, you fix the scale, and at that scale, you check the values of the gauge coupling, and the cutoff has to be well, below or of this order. Okay. When with the gauge coupling evaluated at that scale. And the same here, like this should be evaluated at the same energy scale, the mass and the gauge coupling. Now, still it might seem surprising that you can preserve this along any energy scale. And why we think that's true is because, I mean, originally people thought that maybe it was something just of the deep IR because it's based on black holes, but now we believe that this is valid at any energy scale. And it's because precisely because we don't expect to have a single particle, but infinitely many particles satisfying this. And when you compute, so the corrections, the quantum corrections to the gauge coupling, when you have a single particle, they go logarithmically with the mass of the particle. But if you have an infinite number of them, you sum over all the particles satisfying the gravity up to the species bound, so the quantum gravity cutoff, then this logarithmic running behaves polynomially. So it changes precisely, this infinite sum changes qualitatively the running, so that it's not logarithmic, but becomes linear. And that's why you can satisfy this everywhere along the RG flow. And this is very tied with something I didn't discuss, but let me mention it, which is the emergence proposal, which proposed that, okay, these conjectures like the weak gravity and the distance are telling me that if you have small gauge couplings or large field distances, you're gonna get new light states. What this is saying is that you get that because the reverse is also true. So let me write it here. So small gauge couplings and large distances. So the weak gravity and distance conjecture tells me that this is going to imply the existence of a tower, of a light tower. The emergence proposal, let's put this here. The emergence proposal is telling me that because you have a tower becoming light, by quantum corrections of integrating out the tower, they are going to generate the small gauge couplings and the large field distances in such a way that in terms of the quantum corrected gauge couplings and field metric and so on, the they satisfy these relations with the masses. I mean, it's kind of an RG flow effect. Okay, so it's try to give an explanation for the gravity and distance conjecture by going the other way. Okay, and it's only possible because you have infinitely many of them. Does this answer the question?
Yes. So about the first one, should we G up the same at the same energy? I mean, about London.
Yes. So here you would say that it's at the same energy, and the point is that this should be valid for any at any lambda. Like you can check this for any energy scale, and you evaluate it this, and then it should work.
Yes. Thank you. Thank you.
More questions? Is there anything that people would like to listen today? Anything that you would like to learn? And maybe you have heard about the Swampland program, but you don't know very well what it is. Now is the moment. Otherwise, I will choose. Okay. Well, you can also say it later on if something comes to your mind. Okay. So in that case, let's start. So yesterday, well, these days, yesterday and the day before, we discussed the weak gravity and the distance conjecture. This is the summary of the formulation of the two conjectures, that you must have some new state satisfying this behavior for the mass in terms of the gauge coupling or the field distance. And yesterday we gave evidence coming from string theory for these conjectures, implying that there is always some Taworth states that become light in these limits. Now, today, one of the things I want to do is that regarding the weak gravity conjecture, there are more things that have been done and some loopholes and subtle issues that have been addressed in recent years. So I want to tell you a little bit about it, like for example, what is the correct formulation when you have more than one gauge field and so on. And then I will discuss open questions. Okay, so what are the open questions that we have with these conjectures? And after the open questions, we will take a step back and so I will show you some network of connections between the different conjectures and what are the other Swampland ideas that, even if we have not discussed in detail, are all related to these two conjectures. So we will see how everything is related. Okay, very good. So first of all, I was not very careful with what is the definition when you have more than one gauge field. I'm all the time talking as if there is only one. But of course, in general, we're going to have more than one. So the proper definition is what is called the convex Hall condition. Okay, so the point is, for instance, originally we motivated this as a kinematic requirement to allow all black holes to decay. And you could ask, okay, if I have more than one gauge field, like let's imagine, let's plot here the charge to mass ratio under one of the, imagine that we have two gauge fields. So we have a plane and we put the charge to mass ratio under each of the U1s in one of the axes. You could ask, is it enough to have one particle satisfying the gravity conjecture for each direction? So for each U1, so I just have one particle for each U1 satisfying the gravity. Is this the correct formulation? The answer is no, because the whole point is that you can have linear combinations, right? That are charged, they're both U1s, and the statement should be that any black hole for any charge, even if it's a linear combination, should be able to decay. So if I plot, let's plot here a region, which is the black hole region. Okay, so the if you are inside this ball, your charge to mass ratio is going to be smaller than 1, or if you wish, it's going to be smaller than the charge to mass ratio of an extremal black hole, meaning that black holes can only exist here. Okay, so since they have this super extremality bound, the charge to mass ratio of the black holes live here. Okay, the mass has to be bigger than the charge. So this puts a constraint. And now, if I want any black hole to be able to decay, it's not enough just to satisfy it here and here, because, like, for example, if I saturate it in these two directions, a black hole with a diagonal charge is not going to be able to decay to any particle, because any particle with both directions, I mean, if it decays to the first, let's call this particle 1 and particle 2, if it decays to the combination of 1 and 2, it's not kinematically allowed, because the charge to mass ratio of the black hole is larger. It can be larger than the result of the 1 and 2 particles. I don't know if it can be a bit confusing, but the whole point is that the statement that one has to require is that the convex Hall of all the particles that you have in your theory includes this ball in which black holes live. Okay, so that any direction, I mean, is contained, and any black hole of any charge will be able to decay. Is it clear? Okay, so the statement is the convex Hall, which is like you take all your particles and you just join, okay, the different points. So the convex Hall of the charge to mass ratio of all the states in your theory should contain the extremal region where black holes live. And that's typically something stronger than requiring just the weak gravity conjecture for each of the gauge fields individually. Okay, good. Now, if you want, I mean, the way to understand this more clear is also to work it out. So you can do as an exercise. You can show that, for example, starting let's see, yeah. So if you start with a black hole that has some charge Q1 and Q2 under the two gauge fields, you can show that it is not enough to have weak gravity saturating particles for each U1 independently. Okay. And it's just an exercise, like by charge conservation and energy conservation, you can just show that it's not kinematically allowed. Okay, good. Now, this condition, I mean, this convex Hall condition already give us a hint that it's actually not enough to have just one particle for each U1 gauge field. It seems that we need to have more than one. So it already gives us a hint that the weak gravity conjecture is going to predict more than one state satisfying this condition. And in particular, I will put, if we think of, if we start with a U1 gauge field plus one particle, okay, that satisfies the gravity conjecture, so that the charge to mass ratio is bigger than 1. And so this is the first step. Now the second step is that we compactify the theory on a circle. We can show that the lower dimensional theory does not satisfy the gravity conjecture anymore. So starting with one particle is never enough. The lower dimensional theory does not satisfy this convex hull with gravity condition. Okay, so why is this happening? Well, when I compactify on a circle, we are going to have, after compactification, we are going to have the original U1, okay, that we had before, the original one, plus a KK photon. So now when we compactify, we get more gauge fields. Okay. And you're going to have now states which are like all the Kaluza-Klein copies of your original particle, which are going to have a charge to mass ratio, which is the original charge to mass ratio that they had under the original U1, and another component, which is the charge to mass ratio under the KK photon. Okay. And you can check, I can give you the result. See. Yeah, so all the KK modes, right? They are going to have the original mass plus some mass given by the Kaluza-Klein charge. So this is the KK charge. Okay, so these are all the KK copies. And you can show that this charge to mass ratio is gonna be equal to the original charge that they had, Q over R divided over the mass. Okay. And this, yeah, if you plot it, and I plot here the charge to mass ratio under the original U1, and I plot here the charge to mass ratio under the KK photons, and I have this extremality bound, you can show that all these states, when you change the value of Q, so all the KK copies, are going to lie here. So you are going to have one here, another one here, another one here. But at some point it stops, and then you have another one here, and this is going to cut. If you plot it in mathematics or whatever, you can show that this cuts this extremality region so that you don't satisfy this convex Hall condition. So starting with one particle and considering all the KK copies is not enough to satisfy the gravity conjecture under both gauge fields, the KK photon and the original one. Okay. So the solution is that you must start originally with an infinite tower of particles satisfying the gravity under the original U1. And this way you are going to feel the full ball, like the full extremal region in higher dimensions. So already in higher dimensions, you must start with more than one state. Okay, so this is the argument of why just thinking of consistency under dimensional reduction, you can argue for having more than one state satisfying the gravity conjecture. Okay. Any question?
Yes, I wonder how it is not a function of the radius. I mean, the compactification.
Yes, okay, yes. Yeah, that's a good thing. So actually I didn't, yes. It's a function, so how much you cut this, it is going to depend on the value of the radius. So actually it's true. So let me put the final formula. If you do it carefully, you can show that you can satisfy it only if the radius is very large. So let me call this C, so this is called C, okay. And this is like C0. So if you do it analytically, you can show that it is satisfied if this is satisfied. So indeed, it depends on the radius. The point is that you cannot satisfy it for any value of the radius. So a parametrically large radius in comparison with the mass you will be able to satisfy it. But as long as the radius is a bit smaller, you start cutting this convex hull, this extremal region. So if you want to guarantee that you will satisfy it even in the middle of the moduli space, then you need to start with an infinite number of particles.
Mm-hmm. And there might be a mixing between this KK photon and the ordinary photon, right? I mean the kinetic mixing. So this plot is in the flavor basis, or it doesn't matter which base it is.
I think it doesn't matter. Like the point is that you can diagonalize if there is a mixing, and then write in terms of the new two independent, like orthogonal gauge fields. And then still the point is that you're gonna, maybe it's not like now I'm thinking that I have an original particle here. Now, if it's a diagonal, if there is a mixing, maybe it's in some diagonal combination. But the point is that you just have one particle there, and then the KK copies for the others. So the structure, the qualitatively is going to be the same. You just rotate the picture.
Because in that case, we can have arbitrarily light milli-charged particles under the other U1s. So we are in the safe side, I guess.
Yeah, milli-charge is dangerous. Probably that's another thing. Like
less dangerous milli-charged particles. Not, good enough to
okay, good. Yeah, but I think like even with the mixing, you need to start with more than one in some of the directions, because in the end, what you need here is to generate some sort of lattice.
Yes.
So it's like the KK photon is already giving you a tower, but in the other direction, you just have one, and you're not going to populate the full lattice with that. And if there is a mixing, it will be some combination, but still, you can never populate the full lattice.
That's right. Thanks.
More questions? So let's call this consistency under dimensional reduction. Okay, good. Okay, so what are the open questions that we have? Well, for the weak gravity conjecture, yeah, the main open question is what is the particle? What are the states that satisfy the weak gravity? So just a bit of as a summary, we saw that all the arguments based on black holes typically only imply a mild version of the weak gravity conjecture, in the sense that, you need to have some particles satisfying this. We can even include the convex Hall condition here, but there is no constraint about what is the minimum charge, what is the quantized charge of the state satisfying the weak gravity. Okay. And from the point of view of string theory, and also consistency under dimensional reduction, and well, I didn't say, but like there are works also that show that you can derive this weak gravity conjecture from modular invariance on the CFT, and in those cases you also need to have like a tower or sublattice. So in all these cases, we always need to have more than one state, like a tower, a sublattice of states. So you get infinitely many, but this is not telling us either what is the minimum charge. So when you have a sublattice is enough to be consistent under dimensional reduction. You have infinitely many fields. It's just that it's not that if we have a lattice of states, these are the possible quantized charges. Maybe only some of them are populated. So we have a small lattice within the original gauge lattice. And this is actually enough to satisfy this convex Hall condition, because it's like, I have some sort of lattice along all the directions. But there is it's not strong enough in the sense that it doesn't tell me what is the index of the sublattice. Okay, so again, what is the minimum charge of the first state satisfying the weak gravity conjecture? And this is important for phenomenology, because then if we want to give phenomenological constraints, we need to know what is the minimum charge, which is equivalent to know what is the lightest state that satisfies the gravity, and how important it's going to be in our effective field theory. So this is a very important open question that is not solved yet. I can tell you that from string theory examples, we know like the maximum, I think it's 6, the maximum that has ever been obtained for this minimum charge, which is very small. I mean, still small, it's not like 100 or 1000. But we don't have any general explanation of why that should be the case or general proof. Okay, so this would be something very important for this conjecture. Questions? Okay, regarding the distance conjecture, well, first of all, most of the evidence comes just from string theory, like identifying the towers of states at infinite distance. If we don't talk about gauge couplings, it's difficult to talk about black holes. So all the connection with the black holes, comes only when the infinite distance in field space is equivalent to some weak coupling limit. So I have some gauge coupling and I have states that are charged under it, and then I can run the arguments with the black holes. But the question is, what if, I don't know, is it possible to have an infinite distance limit that is not associated to a gauge coupling? Or even if that's not possible, can we find some argument that does not rely on the gauge coupling, just on the infinite distance by itself? Okay, so this is some open question, like given some bottom-up argument of why large field distances are problematic in quantum gravity. The second open question is the exponential rate of the tower. Okay, so the conjecture just tells me that must decay exponentially with some order 1. But it would be nice to fix exactly what this factor is, because that's also important for phenomenology, right? Because, I mean, all these order 1 factors will matter when we want to give precise phenomenological constraint. So this is actually, I have to say, we are not so far from solving this, because this alpha is actually related to the nature of the tower and the nature of the limit. And if everything is just the compactification or string perturbative limit, we can tell what it is. So we just need to understand, yeah, what are all the possibilities, and then give this exponential rate for each of them. Okay, and would be a sort of a classification job. And finally, something which is really like more difficult is to understand what happens in the presence of a scalar potential. So most of the examples that are studied in string theory are moduli spaces, in the sense that the scalar is completely flat. It's a massless field. But in order to use this for phenomenology, we are interested in the case in which the scalar has some potential, like in inflation. So you could say, okay, what happens if I have a scalar potential? Because then, I mean, originally this is a constraint about the geodesics. But if I have a scalar potential, I can move along more difficult trajectories. So how the distance conjecture gets modified when I have many different trajectories along which I can move? There is always some exponential behavior or not? How do I constrain these trajectories? So what we think is that, I mean, the distance conjecture, the same than before. I mean, we require that the gravity is consistent under dimensional reduction or under the RG flow. So the distance conjecture should also be satisfied under the RG flow, should be consistent under RG flow, meaning that if we are at a very high energy, we are not sensitive to the scalar potential, and the distance conjecture should be satisfied. If we decrease the energy, we get sensitive to the scalar potential, but the distance conjecture should still be satisfied, should not depend on what is the energy at which I'm checking this. I mean, this is because this is like a general quantum gravity constraint. So it should apply to any pseudo moduli space that you get in the IR. Okay, so the point is that as you decrease the energy, you can start integrating out heavy states, and your theory and your moduli space is going to change. So the point is that should apply to any of the pseudo moduli spaces that you can get at any energy scale. Okay. So should apply to the pseudo moduli spaces in the IR, meaning that, I don't know, imagine that you have like some scalar potential, you have some value of the scalar potential. I don't know if I can draw this, but like something like this. So there is a direction, right? Like I have some value, which is like the bottom of my potential, and I have like some runaway. The distance conjecture should still apply to this one-dimensional direction, this one-dimensional moduli space, which is the bottom of the potential. Okay, because if I can just integrate out all the heavy states and I just get this light direction, and this is my new moduli space. Okay, so the distance conjecture, I mean, by consistency under the RG flow, means that it constrains the type of trajectories that I can get. Okay. The possible trajectories and therefore the possible potentials that are consistent with quantum gravity. Why? Well, because otherwise I can come up with counterexamples very easily. I can just think that, okay, imagine I approach some point and indeed the distance conjecture is satisfied, like I get some tower that decays exponentially in terms of this distance, okay, between these 2 points. But now I choose some potential that force me to move like in a very big spiral, right, around this point before reaching the point. So the distance that I travel can be much, much longer than the geodesic distance between the 2 points. So even if the tower was decaying exponentially in terms of the geodesic distance, it's not going to do it in terms of the distance that I travel along the spiral. So that would mean that the distance conjecture is not satisfied when I decrease the energy and I only allowed to move in this spiral because of the scalar potential. So what this is telling me is that the distance conjecture already is telling you that these type of potentials are not allowed. You should not be able to engineer a situation like this. So the values of the potential cannot do these spirals or cannot do these crazy things, such that you increase the distance much more than the distance that was already given by the geodesic. Okay, so it constrains the level of non-geodesicity that the scalar potentials allowed. Okay, and that's why you can give many interesting constraints for inflation, because, like, for example, these spirals are very typical in axion monodromy and models like that. And then you can try to argue that this is not consistent with quantum gravity. Questions?
Sorry, one question. How do you know that the potential you start with is a flat one? I mean, you have modular space of flat directions. Where are they coming from? I mean, the potential you start at the very large scale, large energy, okay, at Planck. So how do you know you have flat directions?
It doesn't have to be completely flat. It can have some energy, as long as the energy, like it can be like some runaway, like it can have some energy, as long as this energy is smaller than the cutoff, no? Like that the energy that I am checking the conjecture. So what I mean is that, like, let's think that this is the scalar potential, and this is phi, right? The point is that I should be able to satisfy the distance conjecture at any energy scale. So I can just fix an energy scale like this one, for example. And then below everything, I mean, if everything that is much lighter than this energy scale, it's effectively massless from that perspective. And therefore the distance conjecture should also apply. So it doesn't matter that you have a small energy. What matters is that there is some infinite distance limit that is not obstructed by the potential. Okay, so if you have something like, take another color, some potential like this that grows up, then there is nothing to tell because there is no infinite distance limit, because even if I roll up, at some point I'm gonna hit the cutoff, so there is no infinite distance limit in this EFT. But if I have some scalar potential that goes down, I have some infinite distance limit that I can describe within the EFT, right? Because the energy is always smaller and smaller. And this infinite distance limit should also satisfy this conjecture.
Does it mean that at high energy scale, you assume that you always have some massless particles?
Well, I mean, if you go to high enough energies, everything looks massless in a sense, right? Like it's just a ratio. Like in physical grounds, it's the same. I mean, mathematically it's different, but in physical grounds, the limit in which you go to a very high energy in comparison to another scale is the same that you are at smaller energy and this is massless, right? What matters is the ratio. I mean, it doesn't matter the absolute value. What matters in energies are always these ratios. So what matters is that the energy, well, let's say the mass associated to the potential over the energy at which you are checking the conjecture goes to zero. I mean, it's very small. That's,
okay.
But as long as that happens, this should apply. Okay, so that's why we think, yeah, like when you have like slowly rolling potential, like in inflation, right? And you have some particles slowly rolling. In principle, if the EFT allows you to go parametrically far away, then this is going to be constrained by the distance conjecture.
Okay.
It actually becomes more and more flat, no? As you go to larger and larger distances. More questions? Okay, so let me mention a little bit phenomenological implications. I'm not sure if Lars already mentioned a bit about the weak gravity conjecture and the actions, but just as a quick summary. So in general, the weak gravity and the distance conjecture are going to constrain theories with small gauge couplings or large field ranges, okay? That's the case in which this constraint, I mean, even if the weak gravity conjecture applies for any value of the gauge coupling, it's only when the gauge coupling becomes very small that it becomes constraining, because then you get new light states. Otherwise, the states that satisfy the conjecture could be very heavy, and they could even be black holes themselves. So it's not really constraining the effective field theory. Okay, so when it constrains the effective field theory is when you go to the limits. And then for the distance conjecture, what we get is a relation between the cutoff in energies and the cutoff in field space in Planck units. So as we said, this puts an upper bound for the field range. Okay, which is given in terms of the cutoff. Meaning that the higher the energy scale at which you want your EFT to be valid, so the larger you need this cutoff to be, the smaller the field range that you can describe. And that's why for inflation, where you need very large field ranges, but still very large energies, this becomes very constraining. So for inflation, at least we need that the Hubble scale is smaller than the cutoff, right? Because otherwise the EFT doesn't make any sense. And this gives us a relation between the field range and the Hubble scale. That, I mean, you can plug, it will depend on what is this exponential rate to be precise, but if this is some order one factor and this is just a logarithmic correction, this is going to be some order one in Planck. And that's why we say that Transplanckian scalars seem in tension with the distance conjecture. Okay, of course, you have to check exactly what is the order one number depending on the nature of the tower and the Hubble scale in your EFT, but it's not going to be much farther or much larger than the Planck scale. And for the weak gravity conjecture, if I am interested, for example, in inflation, the weak gravity conjecture is telling me that for actions, which are like zero form gauge fields, there must exist an electrically charged state, which is an instanton, with a mass, which is like the action of the instanton over the charge, which is the inverse of the decay constant, has to be smaller, well, than Planck units, meaning that, because let me put here, so S is like the mass, this is, and F is like 1/g, okay? So this is the instanton action, and this is the decay constant. So I'm just applying the gravity conjecture. And in case you don't know, like the decay constant is the periodicity of the action, okay? So if we want to keep perturbative, well, not perturbative, if we want to keep computational control, the instanton action must be bigger than 1, because otherwise this exponential suppression doesn't make sense and the computation of the instanton action doesn't make sense, which implies that the decay constant of the actions cannot be Transplanckian. Okay, and this is also why we say that Transplanckian actions such that the periodicity of the action is Transplanckian are problematic. Okay. So the distance conjecture allows me to constrain non-compact scalars, while the weak gravity conjecture allows me to constrain compact scalars like actions. Okay, and in both cases, the distance that you can travel is bounded by some order 1 number, the Planck scale. I mean, of course, this doesn't mean that you can rule out completely. So large field inflation. Okay, so large field inflation is not ruled out, but it's constrained. It's highly constrained. And depending on the specific model, you have to check the constraint more carefully. If you have more than one field, you have to check the convex Hall condition and check all the order 1 factors and see whether it's still allowed or not. And some models will be allowed and some models will be ruled out. Okay, but it's borderline. So it's precisely the sweet spot in which you can give non-trivial constraints. Any question?
Yes, I asked this in the previous session also. For the STC, you choose this bound that the Hubble rate is less than the cutoff. I would expect a Hubble rate less than cutoff squared in Planck units, right? Not this one.
Cutoff
because
square? Why cutoff square?
Yeah, I'm Planck H less than lambda squared Planck units. I mean, the energy density is less than, I would say. So think of Friedman equation, right?
Yes, you're thinking that the gravitational interaction is not too important, right? Like this is sort of the gravitational back reaction in your Friedman equations.
Right, but H is IR cutoff, right? So, I mean, we expect that it is less than lambda. I would expect H must be less than lambda squared in Planck units. I mean, H squared less than lambda to the 4 in Planck units.
Like the potential. You're thinking like this in Planck units, right? Like the whole. No, that the potential is smaller than the cutoff, you mean?
No, I mean H less than cut up to the 4. H squared less than cut up to the 4. H squared.
Okay.
Yeah.
Okay, so that the potential, which is like H squared, right?
This is what I would expect.
Exactly. So what you are expecting is that the potential is smaller than the cutoff.
Mm-hmm.
Right? Yeah, so this is exactly. So there are two possible things that one could impose. Either that the Hubble scale is smaller than the cutoff, or that the potential itself is smaller than the cutoff. This is stronger, requiring that the potential is smaller than the cutoff, and can give even stronger constraints. Like it's gonna change like since it's just a power, it's gonna change like this order 1 number in front of the log, but it's gonna be stronger.
I would say stronger. It is weaker. I mean, this is weaker because H is less than lambda squared in Planck units. So on the right-hand side, we have log squared, something like that. So I would say it is weaker.
Let's do it. We can do it. So let's do it. Right. So here you will have m Planck alpha log m Planck, and then lambda, I replace it, right, by h to the 1/2, right? So there is a, and then, well, the Planck units, I'm not careful, but everything is going to be in Planck units. So it's like the 1/2, I can put it in front. And then you are decreasing the bound, right? Like you're saying that delta phi is more than 1/2 1 over alpha. So it's in times of m Planck. So before we just have 1 over alpha, now you're saying that it's half. So it's a stronger bound. And that makes sense. Like the potential, I mean, typically the scale of the potential is larger than the Hubble scale. So that's why it's stronger to impose that the potential is below the cutoff than impose that the Hubble scale is below the cutoff. It's a 1/2. I mean, it's just 1 over 2. It's 1/2 factor. So that's why it's part of this order 1 that you have to fix. And it's something I have thought about sometimes. I think, I mean, this is like the conservative bound. It's like, at least I know for sure I have to require this, right?
Yes.
And otherwise, I mean, I think there are scenarios in which I think this should be true. There are other scenarios in which it's not so clear that it should be true. It depends on the back reaction and many other things, like how much you can still make sense of it. Like, for example, if it's a recompactification, you can still make sense of it for a while. So I feel it becomes more model dependent. But I completely agree that, yeah, you should take this as the conservative bound, and typically it's gonna be something stronger than this, because also you're gonna get sensitive to the infinite tower even before you reach that scale, right? Like you will get some signatures and like the constraints. I mean, this is like the most conservative thing that you can do, but in general, you're gonna get sensitive to the infinite tower, and probably the EFT is going to break down earlier than this. But then it becomes more model dependent. I think I cannot see a general way to do it, but it would be very nice to do it more generally. But yeah, for each model you have to be careful, because probably it will be stronger. I agree.
Thanks.
More questions? Okay, so with this, I finish these two conjectures, and in the last 10 minutes, we are gonna take a step back and look to the Swampland program as a whole. Okay, so let's take this one. So in this introduction to the Swampland lectures, we learn about the absence of global symmetries, the weak gravity conjecture, and the distance conjecture. And these three conjectures are really at the core of the Swampland program. Okay, these are the three most important conjectures that you have, and play a very important role, because many of the others have been formulated as refinements or generalizations of these three. Okay, so understanding these three very well is very important, and putting them in solid ground and being precise with all the factors and everything is very important to continue making progress. Okay, because it will, any ambiguity that we have in this conjecture will also propagate to the other ones. So we need to have these ones in very solid ground. Now we see that we discussed that actually these three conjectures, even if they were formulated independently, are connected to each other. Okay, so we have seen that whenever the infinite distance is associated to a weak coupling point, the same tower of states satisfying the weak gravity conjecture also satisfies, like this color, satisfies the distance conjecture. Okay, so it's the same tower. It's just that in one case we focus on the dependence on the gauge coupling, and in the other case we focus on the dependence on the field range. But basically it's the existence of the same states. Now it's not clear if it's exactly the same, because still we don't know if there is any infinite distance limit without a gauge coupling. So we need to find out that before unifying completely the conjectures, but they look very similar at the moment. Also, both of them can be understood as kind of refinements of how much you have to break or gauge the symmetries. Okay, so we have seen that the gravity conjecture tells us that the gauge couplings cannot be too small, so it gives us a constraint on the strength of the gauge field that you have to add to gauge a global symmetry. And the same for the distance conjecture, because when we approach this infinite distance limit, we restore some global symmetry. So it tells us how much we can approach, like how close we can get to the situation of restoring the global symmetry. Okay. Now, what about the rest? So in recent years, so these are the oldest one, but in recent years, there have been new formulations of new constraints. I think you have heard from Miguel's lectures, the cobordism, triviality of the cobordism, okay, which is a generalization of no global symmetries by including topological charges that are present in gravity because the space can fluctuate, topology can change, and all these topology changing processes suggest that the more general notion is not a topological operator, but is cobordism classes. It's kind of a generalization of this, so it's also related. And then I think he also saw you explain that if you allow for generalization of global symmetries to include higher force symmetries and non-invertible symmetries, then you can also derive the completeness hypothesis. So the constraint that the spectrum, the charge spectrum, should be complete. That you should have a state for every possible charge. Okay. Now, Lars and Thomas have discussed about the scalar potentials and cosmology. And this refers to this third line of conjectures. Okay, so let me point out here, like all this is about exact global symmetries. This second line is about constraints on the field spectra, like saying that there are new states that appear. And this third line is about constraints on the scalar potential. And these constraints are always motivated actually by the existence of the towers satisfying the gravity and the distance conjecture. So you can ask, okay, now I have new states. What is the effect of these new states in my EFT? And this is what gives rise to these relations here. Okay, so just very quickly, since it's not the goal of lectures, but in case, I think it's a nice summary, let me tell you what they are. So what I wrote here is the non-SUSY ADS conjecture, in the sense that non-SUSY vacua are at best metastable, so that any vacuum, if it's not completely supersymmetric, should eventually decay. And you can motivate this by applying the weak gravity conjecture for codimension 1 branes, so for domain walls in your theory. So if you apply it, then it would tell you that you have a charge to tension that is bigger than 1. And when you have a domain wall with a charge that is bigger than the tension, it's gonna give rise to a bubble instability. Because the cost of energy of expanding the bubble is smaller than the electric repulsion, because the charge is bigger than the tension. So it's a bubble that will expand and will describe an instability. So you can use the weak gravity to motivate that whenever you break supersymmetry, you will always have some unstable vacuum. And that's because we only expect that the weak gravity conjecture is saturated when you have supersymmetry. And also there is another connection actually with cobordism here, because all these, I think Miguel mentioned a little bit, the existence of end of the world branes and bubbles of nothing. So it seems that the absence of global symmetry already is telling us that there is no topological abstraction to have a bubble of nothing in my theory. And this is also going to describe an instability when the vacuum is non-supersymmetric. Okay, so this was one. The de Sitter conjectures, I mean, I'm gonna explain much, but the point is that we expect that at least when we approach these infinite distance limits and we get these towers of light states, they are going to have an effect on the scalar potential such that they generate a runaway. So at the asymptotic limits, one gets that the slope of the potential is bounded, okay, such that you get these runaways and you don't generate any vacuum. And that's because of the presence of this infinite tower of states, okay? So this conjecture is very well motivated at the infinite distance where we have this tower of states, and it's not clear at all what happens in the middle of the bulk, okay? This is under investigation. And then finally, the ADS distance conjecture, which probably Thomas discussed, is the statement that it's not so easy to get scale separation in ADS. And that's because that also comes from the distance conjecture, right? Because the point is that what they saw is that the limit in which the cosmological constant goes to 0 is at infinite distance in the space of field configurations of the metric. So in metric configurations. So if you generalize the distance conjecture to apply not only to scalar fields, but to any field, including the metric, then you would conclude that you must have some tower of states that, well, the distance is like log of lambda. So when you put it in terms of the exponential, you get just that goes polynomially on the cosmological constant to some power. And if alpha is bigger than 1/2, this means that there is no scale separation in the sense that, for example, if I am in ADS, the Hubble scale, the scale associated to the ADS is going to be of the same order, at least, than the size associated to the extra dimensions, because this is going to be like the KK tower, right? So like you have new tower of states that suggest that there are new dimensions and they are of the same order because the KK mass is of order the Hubble scale. So understanding what is this value of alpha is crucial, is very important to understand whether there is scale separation in ADS, which is also important for holography. Okay, and everything boils down to this factor. Okay, so it's like the order 1 factor of the distance conjecture. Okay, we need to understand what this factor is to understand if there is scale separation. Okay, any question about this?
I have a question.
Yes.
Why is this non-SUSY instability condition mentioned only for ADS? I mean, bubbles of nothing can happen in the sitter as well, isn't it?
Yes, indeed. So this is for every vacuum. So originally it was mentioned for ADS, and that's why I put here this ADS, but it's very misleading. The reason why it was original for ADS is because in the sitter, I don't know, it's kind of accepted, or everybody kind of expects or believes that even if there is a de Sitter vacuum, it's going to be metastable. Like you cannot have completely stable de Sitter vacuum in quantum gravity. So it's not so surprising. While for the case of ADS was surprising when this conjecture appeared, because people thought that it's completely fine to have a non-supersymmetric vacuum in ADS, which is completely stable. So since this was more surprising, the emphasis was given to the ADS. Okay, but the presence of bubble of nothing and all these instabilities apply to even if it's Minkowski or de Sitter. So it should be in general. So the right statement is that, yeah, whenever you bring supersymmetry, the vacuum should eventually decay.
I see. Thank you.
More questions? Okay, so this is a map, okay, of the conjectures. Just to give you an overall idea, I want to remark that one of the most important things in recent years is not the definition of new conjectures, but the relations that we are discovering among the conjectures that hint that they might be all just different phases of the same underlying quantum gravity principles that we are starting to discover. Okay, so it's the most important thing is actually to understand these connections and try to make them more precise. And just gonna finish, put here, well, I had like some comment that we have to approach this from all possible approaches, like string compactification, black holes, holography, positivity bounds, topological operators, whatever you like. We need to gather evidence for all this, because in the end, all this Swampland program, I think it's good news for our universe, in the sense that not everything goes right. This is the main message of the Swampland. There are new constraints that you need to satisfy, and this can have important implications. And I mean, it's difficult to get a general proof, but it can have a huge impact. So it's like new quantum gravity constraints that we can use for phenomenology. And it's all using this UV-IR mixing induced by gravity. Okay, so it's something that in the next years we have to understand much better, like how to make precise this UV-IR mixing, and whether, for example, this can solve naturalness issues of our universe. So I didn't discuss much the phenomenological implications because this was some lectures about introduction to the Swampland, but you can also find more details in some of my lecture notes and other lecture notes in archive, and see how we like this precisely because we think can have an impact for the universe. I hope that you enjoy it and that you learned something and that you got motivated to work on this in the future. So thank you very much for your attention.
Thank you very much, Irene. So we have time for more questions, please.
Excuse me.
Yeah.
So is the conjecture about the Hessian of the potential also only asymptotically correct so far?
Yeah, the second derivative, right? Yes, I think the expectation is that all the evidence that we have for it only comes from the asymptotic limits. So we cannot tell whether it's going to be valid in the bulk. I think it's only, at the moment, we only have real evidence for it asymptotically. So the expectation is that, both these the condition, the first derivative and the second derivative are valid asymptotically. And maybe what happens in the middle of the bulk is that you can still get some de Sitter vacuum, but it's short-lived. So this is what goes along the lines of the TCC, like another conjecture, that puts a bound on the lifetime of the de Sitter vacuum.
Thank you. And another rather philosophical question is, do we assume all the the theories in the Swampland and in the landscape are continuously related, such that if we send M-Planck to infinity, we don't have Swampland constraints anymore?
Yeah. I mean, all these constraints should disappear if you send M-Planck to infinity. It's really important that you keep the Planck mass dynamic finite, so gravity is dynamical. And it's also important that we are in dimension bigger than 3, because otherwise gravity is not dynamical either. Okay, so it's all about higher dimensions and dynamical gravity. And the expectation is that, like everything probably is connected. And we have to identify what are these principles that would reproduce everything. So what is the minimum set of principles that can explain all these features that we observe? And this is under research.
Thank you very much for very interesting lectures.
Thank you for your questions.
Hi, Irene. Thank you for great lectures. May I ask on the last point that you mentioned about the UV-IR mixing and naturalness problem. So is it going to be not a problem if we consider that, or we are going to solve this problem? I'm aware of that work by you and Luis, that there is a mixing between the electroweak scale. I mean, there's a relation between electroweak scale and neutrino mass and CC and the Planck mass. So in that picture, we know that there is a connection. The electroweak scale has to be like 100 GeV. So because we are not in a swampland. So
Yes.
I mean, this is a realization of this picture that UV and IR are mixed. And
Yeah, exactly.
This case. So I wonder if it's going at the end of the day to be not a problem at all. I mean, naturalist problem is not a problem. I mean, in the Wilsonian picture that
exactly, I think that's the point. Like that, this logic of naturalness have to be changed in the sense that it really assumes two things. It assumes that the whole space of parameters is allowed, and then you ask, okay, what is more natural or not natural, and so on. And it assumes that there is a separation of scales, so that you don't want the physics to be very sensitive to the UV. And whenever it's too sensitive, then you say that it's not natural because you have fine tunings and so on. So this changes in the swampland because first, not the entire space of parameters is allowed. And I think this is one of the main things. And why it's so constrained is precisely because there is this UV-IR mixing and you can have a really big impact on the IR. So the way I see it is that, yeah, it's just that first you have to understand what is the space of parameters that is consistent. And then you can apply the logic of naturalness there if you want. But it's gonna change from what we do in a Wilsonian approach because you are starting with a different parameter space. And yeah, in these works, that's what we saw, that there is a correlation coming from quantum gravity such that a big part of the parameter space is ruled out. And therefore the maximum value that you have for the Higgs wave is given in terms of the cosmological constant. So for our universe, it's going to be of order the TV. And it cannot be larger than that because larger than that is not consistent with quantum gravity.
Because another standpoint could be that we have this unnaturally small Higgs mass at the IR because we are free to choose anything in the UV, and it has to be chosen very carefully. Now we say that the boundary conditions cannot be chosen cannot be anything in the UV.
Yeah, exactly.
You have a very narrow region that we are not in swampland, and if you pick that narrow region and we compute the running, there would be no problem at all in the
Exactly. That's the idea. That if you start with the right boundary conditions and constraints, you can still apply quantum field theory. I mean, it's okay. But then, yeah, since the space is much smaller, you are not. I mean, probably you are solving all these naturalness problems because then it's the only option that you get, or I don't know, like it becomes natural. Yes, that's the idea.
Thanks.
It's like, for example, if like one example also is that one that we have in string theory actually, like typically for the one loop energy, right? You would say that can get super large. This is a naturalness issue in QFT because have contributions from everything. But for example, when we do this type of one loop computations in string theory, like in heterotic non-supersymmetric theories, like SO16 cross SO16, and you sum over the infinite number of string modes, the result is not infinite. It gives a value which is the mass, the scale of the first massive state. So, and that's because of the structure of, right, all the tower and everything. So this structure is really important, and that's how in the end you don't have fine tunings, but just it's natural because of the structure behind. So that's something I think we have to understand much better and find more examples and make it more concrete because it can be important.
Okay, any other question? Well, thank you very much, Irene, for very clear and interesting lectures. We hope to see you in person in Tehran for our future program. Thank you very much.
Thank you very much for organizing this. It's very nice. And for the invitation.
Thank you. So we'll back in less than 20 minutes to hear Kamran Wafa's lecture. Okay.